the extension of a spring is affected by the load attached. Figure 1.1 shows the apparatus. So you can see the apparatus is there 0 cent. This is a meter rule. Vertical meter rule is placed. Meter rule means that it is 1 meter long or 100 centimeter. So at the top we have 0 and at the bottom we have 100. The meter rule is clamped in the position as shown. So you can see the position of a meter rule or a meter scale. Write down the scale reading in millimeter. Keep in mind they are asking scale reading in millimeter for the top reading and for the bottom. So can you state, you can use a screen annotation. What is the top reading? And what is the bottom reading? What is the top reading here in millimeter? This is in centimeter. We will multiply by 10 to convert into millimeter. So what is this reading? The first mark. This is 44. This is 44.12. So before 44, what will be the reading? It will be 43.9, and that is 43.9 is actually in centimeter. So this is 43.9 centimeter. So 43.9 centimeter, but in the space we have to write in millimeter, so we should multiply by 10 to convert centimeter into millimeter. So it will be 439 millimeter. What about the bottom reading? So this is 45, 45.1, 45.2, 3, and 4. So this is 45.4 centimeter. But again, we have to convert into millimeters, so we'll multiply by 10. So when this 5.4 is multiplied by 10, what we will get? We will get 454. The next part, use the two readings, calculate L naught. L naught means original length. So like what is this length we have to calculate? L naught here refers to, or L0 means when nothing is attached, no load is attached. So this mark was 439 millimeter and this mark was 454 millimeter. So how much is this length? So how I can work out this length? So if I subtract the two values, 454 minus 439, the difference of the two values will give us this length, which will be in millimeter. So L naught is basically length of the spring when no load is attached. That is called L naught. And in the question they said that use the two readings, calculate the L naught and record in table 1.1 when the load is 0. So when the load is 0, this is a table 1.1. So when the load is 0, how much is this reading? This was 15. In the part B, the student suspends a load of 0.2 Newton from a spring and he records the length in a table. Use the equation. So even in paper 6, you don't have to learn any equations. They will give you the formulas. You just have to use the formulas to calculate certain parameters. So use the equation E, the extension, equal the new length minus the original length, L minus L naught, to calculate the extension of a spring and record the values. So how to get the extension of a spring? This was 15, we already did. So this is the original length and this one is a new length. So when I subtract these two, so new length minus original length, so it will come out to be 2 here. Then complete the extension column. Complete the column heading. Column heading means like this part. Like they mentioned, load is in Newton, length is in millimeter, and so how much is in extension? So if length is in millimeter and when we are subtracting a length to calculate the extension, so what will be the unit of extension? The extension will also be millimeter. So even you just write millimeter here, you will score 1 mark. Then student attach different loads here. You can see different loads are attached, and we already completed the column. We have to plot a graph extension on y-axis. So we have to complete this extension on y-axis and load on x-axis. So whenever you're plotting a graph here extension on load on x-axis and extension on y-axis. Always write, like example, as I mentioned here, extension is on y-axis. So you will write E, the extension, and what is the unit of extension? Millimeter. So E slash millimeter, the unit. And you're plotting a load on x-axis. So L stands for load. And what is the unit of the load? Newton. Then you have to select a scale according to the values given in the question. The load is from 0 to 1. And extension is from 0 to 13. So try to expand the scale so that you can cover 70% of your graph paper. Like your scale should be suitable scale so that when you plot a graph, you should cover 70% of the graph paper. So load minimum value is 0. It started with 0 and the maximum is 1. I have to zoom in just to read the values here. So we have extension in millimeter and we have load in Newton. And the maximum value of the load is 1. So if I select this is 0.25, this is 0.5, this is, or if I select 0.2, 0.4, 0.6, 0.8 and 1. So it is like more than, I'm covering more than 70% on x-axis. So it started with 0, and this is 0.2, 0.4, 0.6, 0.8 and 1, and then 1.2 will be there. And on x-axis and y-axis, maximum value I need 13. Like my scale should cover 13. So if this was 2, 4, 6, 8, 10. So this one is 2, 4, 6, 8, 10, and then, or I can reduce. So try to utilize more space, expand your scale for the axis. So if 0 is there, 2, 4, 6, 8, 10, 12. And the last point, that will be 14. Then we will plot, we'll use the values from the table. So when load is 0, extension is 0. When load is 0.2, extension was 2. This value was 2 here. So 0.2 and 2. You can either use a dot or you can also use a cross to mark the point, but better use a dot. The reason is that so you can easily identify when you want to plot a best with straight line, so you can identify the positions accurately with a dot rather than cross. So we put a dot. The second part, when the load is 0.4, the extension is 5. So when load is 0.4, the extension is equals to 5. So it is between 4 and 6. So this one is 5. The third point, When load is 0.6, basically it's a fourth point, but the first point is 0 and 0. 0.6 and 8. So that is 0.6 and 8. Then when it is 0.8, it is 10, and then 13 is there. So when it is 0.8, it is 10. And when it is 1, it is 13 somewhat in this region. Because this is 12 before that. So these are the points 13, 13. I did not mark the 13 because I use this scale here, which is easy to read. But you should mark 13 as well. Then the next part, what we have to do, you have to draw the line till 10. It is obeying the Hooke's law. Force and extension are directly proportional. So whenever you're use thin lines. So force and extension are directly proportional. And then the last point, it will be a bit curve because 13 is not in the same proportion. That's why it will be a bit curve. The next part, so that was done. That was a graph. Figure 1.2 shows this unstretched spring. Like this is a spring which was not stretched. Like there's no load attached. And the spring with a load is there on the right hand side. On the figure, clearly show the distance L naught, L in extension. So what is L naught? You can see at the beginning of the experiment that L naught or original length from the start of the hook till the end. So that is L naught. So from the start till this point, that is, you have to clearly label L naught. So this one is equals to L naught. Then we have to measure L. We measure from same point. So this will be L. The starting and final position for L and L naught should be same. Only the difference is their lengths will be different. So this is L and this one is L naught. And how much is the extension? Extension means increase in the length. So according to this figure, what is the extension? So this part is representing the extension, which we say E. So moving on to the second question here. A student investigate the resistance of resistor in different circuit arrangement. Here, X and Y are connected in series. There's a voltmeter is connected in parallel to X and ammeter is there in series with the circuit. Then student measure the potential across Vx and so write down the reading, include a unit for a potential and a current or a resistor where appropriate. So what is the reading on the voltmeter? What is the reading here? What voltmeter is reading? How much is this? The reading on the voltmeter? Yes, what about the reading on the voltmeter? Each line is representing on the voltmeter, each line is representing 0.2. So like this is, yeah, that's right, 1.2, because here is 0.2, 0.4, 0.6, 0.8, 1, and then after 1 there is first line. So the reading on the voltmeter is 1.2, and that is volts. Now what is the reading on ammeter? Each is representing, because 10 lines are there between 0 and 0.2, there are 10 lines. So it means each line is representing 0.02. Yeah, that's right. So that is equals to 0.26, because each line is representing 0.02. So there are 3 lines after 0.2. So this is 0.24, because there this is 0.2. So this will be 0.22, 0.24, and 0.26. So this will be 0.26, and the unit, it is ampere. So one of the value is 1.2, another value is 0.26. Then the next part, as I mentioned, you don't have to learn any formula for paper 6. They will provide you the formulas. So this value was 1.2 volts, and this one is 0.26 ampere. Calculate resistance Rx. And what is Rx? The resistance is equals to voltage divided by current. So voltage of X divided by current of X. So what is the voltage of X? That is 1.2. And how much is the current of X? That is 0.26. So 1.2 divided by 0.26. So 1.2 divided by 0.26, that is equal to 4.615, or I can say 4.61. Yeah, or 4.6, I can say. Better write your answer in 3 significant figures. When you're writing your answer, try to write your answer in 3 significant figure in exam. 2 is fine, but 3 is more accurate. So we'll write as 4.62. Follow the rule of rounding off. So 4.62, and unit of the resistance is ohm. So that will be omega. The next part, student connect a voltmeter and he record the voltage of Y and X, and he get the resistance of Y and X, that is 10.4. And then he calculated the resistance of Y, which is 5.78. State whether, and what theory, and she state, what student state, she state that Rx means resistance of X and Y, the combined resistance of X and Y. She calculated, this is a combined resistance of X and Y, and this one is the resistance of Y. State and explain whether Rx and Ry can be considered equal within limit of experimental accuracy. Like the Rx, when we calculated Rx in the previous part, it was coming out 4.62. And when we calculate Ry, according to what they provide us, Ry is equals to 5.78. So Rx is equals to 4.62 and Ry is equals to 5.78. Can I say that these two resistors are equal? Like can I say Rx is equals to Ry? We cannot say, because you can see 4.62 is not equal to 5.78. So simply what we will write here, we will write no. The two within limit of experimental accuracy, two values have a greater difference between them. Like they're far away from each other. Like 4.62 and 5.78 are not within the limits. If, for example, if one of the value was say 4.9 and another value is 5.1, so I can say they are equal because 4.9 can be rounded off to 5 and 5.1 can also be rounded off to 5 as well. But in this one, Rx and Ry cannot be equal because they have a greater difference between them. Then a student connects a resistor Z in parallel to resistor X. She connect a voltmeter, record X and Z, voltage of X and Z, potential across the combined resistance of X and Z, draw a circuit diagram for this arrangement and label X, Y, and Z. So what we have to do, look, instead of drawing the circuit here again, I will use the previous circuit. Read the question as they mentioned, a student connects a resistor Z in parallel to resistance X. So first part, what I should do? So I need another resistor parallel to X. So resistor Z. Even I can connect like this. That is true. That is right. Or I can connect in this manner. That is also correct, because this shows that the two resistors are in parallel. And voltmeter is there, so I don't have to draw a voltmeter. But in exam, because they provide you the space, the whole copy of this circuit, you don't have to draw here. You have to draw the space they provide. So this is a space, provide the circuit diagram. So you have to draw in this part. But just to save the time, I just use the circuit to explain that where I should place Z. So Z should be in parallel to, voltmeter is always in parallel. Voltmeter cannot be in series. So if I connect a voltmeter, I want to connect a voltmeter. We cannot connect a voltmeter. So if I connect Z here and I connect voltmeter like this, that will be wrong. Why it is wrong? Because voltmeter should always be in parallel. Same thing, if I connect Z here, that is also wrong. Because voltmeter is always in parallel to the component. So there should be a separate connection when we connect a voltmeter, and ammeter is in series. Then a student record the voltage of X and Z, that was 0.8, and recorded the current in X and Z 0.36. Then calculate the resistance of X and Z. So how to calculate the resistance? Vxz, voltage of Xz is 0.8 and current of Xz is 0.36. So 0.8 divided by 0.36. What's the answer for this? When we divide 0.8 with 0.36. So 0.8 divided by
2.2.
2.2. So 2.2 is the resistance of this part. Then the last part, another student does this experiment using a set of 3 identical resistors. His result shows that within limit of experimental accuracy, the combined resistance of 2 identical resistors connected in series is 4 times the combined resistance of same 2 resistors in parallel. To test whether his results are true for other values, he does the same procedure with other set of 3 identical resistors. Suggests the value of a resistance he could use to reach the conclusion during 1 hour experiment. Look, what happened? There is another student and he's having 3 identical resistors. What he did, his result shows that the within limit of experimental accuracy, the combined resistance of 2 resistors, 2 identical resistors in series, like he changed the arrangement. So when he finds the combined resistance of 2 resistors in series is 4 times the combined resistance of same 2 resistors in parallel. So when he connect the 2 resistors in parallel, the resistance is 4 times the combined resistance when they are in series. That is what his experiment shows. Now to test whether his results are true for other values of a resistance, like he want to repeat the experiment, he does the same procedure with other set of 3 identical resistors. So he used another set, like maybe for identical, that what is the meaning of identical resistor? Means they have the same resistance. So suggests a value of a resistance he could use to reach the conclusion. What value of resistance he can use? Like first one he did already. So what else he can use? He can use 5 ohm resistor. Like he can use resistors of 5 ohm. He can use resistor of 10 ohms. He can use resistors of 15 ohms. And he can use resistor of 20 ohms. Like first all 5 ohm resistor, then all 10 ohm resistor, then all 15 ohm resistor, and then all 20 ohm resistors. So even you can mention, he can select any value of a resistance from 1 to 20. Any value he can select, at least 4 sets should be there. So you can select any value like all 5 ohm, all 10 ohm, all 15 ohm, or all 20 ohm. So you just have to tell here, you just have to answer here that suggest value for the resistance he could use. So what values of a resistance he can use? He can use maybe 5 ohm, maybe 2 ohm, maybe 3 ohm, maybe 10 ohm, any values. And he should have, whenever we do an experiment, like we should have more sets of a result. So when you have 4 to 5 sets, that will be a more precise experiment, accurate experiment. So he should have about 4 to 5 sets of different resistors, and he can test his theory that according to his theory, that when resistors are connected in series, their resistance is more as compared to resistors connected in parallel. So you don't have to prove his theory, you just have to mention that what resistance student can select and how many sets he can choose.